Good afternoon, everyone. Thanks very much for giving me such a great chance to talk about our recent studies. In the next 40 minutes or so, I will be talking about precipitation of radiation belt electrons, but mainly focus on their effects in the atmosphere. This is mainly about two of our recent studies performed towards better understanding of Bremsstrahlung X during energetic electron precipitation. Let me start with a brief introduction of the background. As you know very well, energetic electron precipitation causes significant disturbance to the radiation belt dynamics, the coupling between the magnetosphere and atmosphere, as well as atmospheric chemistry. The energetic electron precipitation is believed to be one of the main loss mechanisms for particles in the radiation belt and controls the balance there. And on the atmospheric side, precipitating electrons can generate a massive amount of ionization production through direct interaction with air molecules. And these newly generated ion and electron pairs can further interact with neutral species and produce reactive odd nitrogen and hydrogen, NOx and HOX for short. HOX has a pretty short lifetime, but they can deplete ozone by as much as 90%. And NOx is more stable, but they can be transported into the stratosphere and destroy the ozone concentration there. Given this importance, this is a figure that I got from Randall Anno 2015. It shows the NOx enhancement measured by satellite. Given the importance, various instruments have been designed for the measurement of precipitating electrons, including satellite, very low frequency, and balloon measurements. Each has its own advantage and limitation. These are some satellite measurements by the diameter satellite. Satellite measures particles in the radiation belt, but they cannot resolve the pitch angle distribution of those particles and cannot determine the truly precipitating fluxes. As I mentioned, the precipitating electrons can largely enhance the electron density in the D region ionosphere, and which is the effective reflection altitude of VIF waves. And this enhancement can be detected using VIF receivers and ground level, but the flux and energy distribution of source precipitating electrons cannot be retrieved using the change in the VIF magnitude and amplitude and phase. In addition to ionization production and chemical changes, intense X-rays can be produced through a process called Bremsstrahlung radiation. It's a process in which when electrons are deflected by air molecules, a photon is generated from the conservation of momentum and energy. There are like many different definitions for gamma rays and X-rays depending on the energy and how they are produced. Here, I call all those Bremsstrahlung produced photons as X-rays. These X-rays are very energetic, they are not charged and more penetrating. They can deposit energy and altitudes as low as 20 kilometers or even 10 kilometers, depending on the energy of source electrons. And because of this, balloons have been launched to measure these X-rays and altitudes around 30 kilometers. And the emission of these Bremsstrahlung X-rays into the lower atmosphere is like an optical thick experiment because the air density is increasing with decreasing altitude. A significant fraction of those X-rays would be back scattered into the outer space and being detected by satellite. The main focus of our study, of this study, are those Bremsstrahlung X-rays back scattered into the space. And the goal is to better understand these Bremsstrahlung X-rays and develop a method that can be used to estimate the size and flux of precipitating electrons using X-ray measurements. For this goal, we used two Monte Carlo models, including the energetic precipitation Monte Carlo model, which was developed 2 decades ago at Stanford University, and another little Monte Carlo model that I wrote is the Monte Carlo model for photons. We mainly focus on 3 measurable characteristics for those Bremsstrahlung X-rays, including the spatial distribution. That is the X-ray flux and different locations. X-ray images, basically energy deposition in different pixels of X-ray detector, as well as the energy spectra. Actually, these 2 models are originally designed for the studies of energetic radiation from thunderstorm and nitrogen discharge, but we have recently adapted them for the studies of energetic electron precipitation. We have validated this set of numerical models by comparing with previous results. This figure shows the comparison of ionization profile, that is the altitude profile of ionization production with Fang et al. 2010. It's pretty clear that our simulation results for both 100 keV and 1 MeV are pretty close to Fang's calculation. There is a slight difference which might be explained because of the background atmosphere density. We have also compared the simulation results with Fram et al. 1997. Different from the previous figure, we see 2 peaks here. The first peak, around 100 km, is produced by electron direct impact ionization, and the second peak is much lower, around 30 km, which is produced by Bremsstrahlung X-rays. We see that our simulation results of the 2 peaks are consistent with Fram et al. 1997. We have also compared. Oh, it's actually, this is, Fram actually took some satellite measurements and used the integrated energy spectrum and put that in Monte Carlo simulations with some other model, calculated the ionization production is for a given period of time corresponding to satellite measurements. It's probably averaged for some time. Yeah, it seems like aurora flux, yes. Yeah, exactly. We have also compared the simulation results with giant simulations. It's not shown here, but the results are pretty consistent. To better understand these Bremsstrahlung X-rays, we need to know first and which altitude they are produced, and as well as like how they are redistributed in the atmosphere. We have simulated the Bremsstrahlung production by monoenergetic beams of precipitating electrons. This figure shows the altitude distribution of Bremsstrahlung production for different precipitating energies. The red line here shows the peak altitude of Bremsstrahlung production. It's expected that the peak altitude decreases as increasing energy because electrons are becomes more penetrating. This is the Bremsstrahlung production. The simulation results of Bremsstrahlung transport is shown in the red panel. This figure specifically shows the spatial distribution of X-rays produced by continuous precipitation of 1 MeV electrons, and which is a slice of the results here. We see that most of the X-rays are produced around 50 km. A large amount of those X-rays are emitted into the lower atmosphere, but they are absorbed above 20 kilometers because of the air density. And a significant fraction of those X-rays are actually back scattered into the space. And this is the main focus of our study. We mainly investigate X-ray images and energy spectra. To calculate X-ray images, we need to make use of the trajectory of those X-rays before being detected. This figure, as shown in this figure, each point here represents a scattering by air molecules. We even see this kind of like crazy photon, which first goes horizontally for several tens of kilometers, and is then scattered back to the source region. The trajectory of X-rays, using this kind of information, we can determine the angle from which X-rays are recorded by the detector. And this kind of incident angle can be then converted into energy deposition in different pixels of the detector, and that's the X-ray images. This figure shows the X-ray images in the log and linear scale, and the X-ray camera is assumed to be located at 35 kilometer altitude. We have also simulated the X-ray images at 40 kilometer altitude, slightly higher in altitude and closer to the source. The results are pretty similar to those at 35 kilometer altitude. The bottom panels here show the simulation results at 500 kilometer altitude, representing satellite measurements. Different from these figures, the energy deposition in the X-ray images at 500 kilometer altitude is a bright spot. This is mainly because those X-rays recorded by satellite experience much less collisions than those recorded by balloon. And we know exactly, for example, at which altitude those Bremsstrahlung X-rays are produced. We can then convert this bright spot into the area of Bremsstrahlung source and to the production altitude. The source is a pretty straightforward geometry problem here. The source is found to be a 10 kilometer by 10 kilometer square, which is pretty close to what we used as the input of Monte Carlo simulations. The point here is because of the decreasing air density, photons that are back scattered into the space experience much less collisions or even no collisions, and the space-based X-ray imaging can be then used to roughly estimate the size of the precipitation area. We have also calculated the energy spectra at different altitude as produced by monoenergetic beams of electrons. This figure, the top left panel, shows the energy spectra of those source photons that are initially produced in the atmosphere. The second and third panel shows the energy spectra that would be measured at 35 kilometer and 500 kilometer altitude, representing balloon and satellite altitude. The bottom panels show the same results, but only for selected energies. A question I ask myself is like, what fraction of the total precipitation energy can be received at different altitudes? For example, then I plotted this figure. This figure shows the fraction of the total precipitation energy that is converted into X-ray production, and the fraction of the total energy that can be received at balloon and satellite altitude. The sum of the red curve and blue curve is basically the black curve. The takeaway of this figure is it is better to use satellite measurements of X-rays if we want to monitor precipitating electrons with energies below 800 keV, basically because relatively more energy would be back scattered into the space. These are pretty much like monoenergetic simulations for a real precipitation event with a given energy distribution. The energy spectra of X-rays is basically a weighted sum of those monoenergetic beams from different energy components. Basically, we can calculate that using this formula. For example, here, if the precipitation source has an exponential energy distribution, the black curve here, we forward simulated the precipitation event and calculated the satellite measurements of X-rays at 500 kilometer altitude. That's the black curve here. We tried to fit this curve using the monoenergetic simulation results. Basically, we try all possible combination of fitting coefficients. The set of fitting coefficients that minimizes the sum of sum of square residues is determined as the best fit, which is the green sine curve here. That's the best fit. The fitting coefficient tells us, like for example, the number of particles precipitating electrons in different energy beams, and these are shown as the sine curve here. We see that the weighted sum of monoenergetic beams can very well explain the simulated measurements, and the best fitting coefficient is pretty close to the true source we used in Monte Carlo simulations. And we have evaluated the performance of this inversion method using in terms of ionization production in the atmosphere. We calculate the ionization production in the atmosphere as produced by the true and derived source. They are shown as the black and sine curve here, and we repeat this calculation for 10 times, and the results are the dashed lines here. It's pretty clear. The difference between the ionization production of the true and derived source is like 10% or 20%. We repeat this calculation for different energy distributions, uniform, exponential, with different E0s, and we repeat this calculation for measurements and different altitude. For example, satellite and balloon measurements. And it's pretty clear here from the last column that for both uniform and exponential distribution, and for both satellite and balloon measurements, the ionization production by the derived source is pretty close to that of the truth. This actually summarizes the first study that we recently published. The second study is sort of like an application of the first one. Terrestrial electromagnetic energy can escape the atmosphere, interact with particles in the radiation belt, and cause precipitation. A major source of the electromagnetic energy in the atmosphere is lightning discharge. Lightning mainly emits radio waves in the very low frequency and low frequency range. A small fraction of those VF waves can escape the atmosphere, following or not following the field lines, and they can cause precipitation. And these VF waves are called lightning-generated Whistler waves, and this phenomenon is called LEP event. LEP was actually first observed almost 3 decades ago, 3 decades ago, by the S81 SEEP satellite. This figure shows the satellite measurements of precipitating fluxes. And the top panel here shows ground-based measurements of lightning-emitted radio waves with unicorn name spherics. It's pretty clear. This kind of sharp rise of precipitating fluxes is very well lined up with these spherics, which means these precipitation events are caused by the lightning discharge. LEP was mainly studied using satellite or VLF measurements, but back in 2013, the balloon array for relativistic radiation belt electron losses measured a series of intense X-ray pulses in Antarctica. There is a total of 11 isolated X-ray pulses, as shown here. These are the photon counts versus time. The duration and temporal structure of these events are fundamentally different from typical precipitation event, but the sharp rise, the linear rise, and exponential decay is actually pretty similar to the spherics emitted by lightning discharge, which means these balloon measurements might be X-ray signatures of LEP event. To study these, we first try to find out the source lightning discharge from ground-based detection network. The left figure shows the Gauss image of active storms around event 1. And we have also checked this is the balloon location, and this is the geomagnetic conjugate point. We have also checked the UNEN data, which is a worldwide lightning detection network. The blue points here show all those lightning discharges between 9 and 12 UT, and the red points are those candidate events that we found for the balloon measurements. Candidate means close correlation in time and high peak current, which is required for producing X-rays. We know the location of balloon measurements is pretty much around L4, but we are uncertain about the parent lightning discharge. We performed a series of parametric studies. For example, we simulate lightning discharges at different latitudes. We calculate the precipitation and different L values. And then we can determine from this set of simulations like which lightning discharge can best explain barrel measurements, and is also consistent with the lightning database. Yes, we do. Actually, this kind of structure are caused by the multiple bounces. So this set of simulations include ray tracing with particle interactions in the radiation belt, Monte Carlo simulation of electron precipitation, FDTD simulation of VRF waves, and this figure shows the simulation results of the first 2 steps. Specifically, it shows the flux of precipitating electrons and different L values as a function of time and energy, and as produced by a lightning discharge at 25 degrees latitude. The middle and red columns show the same results, but produced by lightning discharges at 35 and 45 degrees latitude. The bottom panels show the integrated fluxes. Similar to the first study, we simulate the production and transport of Bremsstrahlung photons. For example, this figure shows the altitude distribution of Bremsstrahlung production. Basically, the altitude and which photons are produced, X-rays are produced. This is actually the corresponding energy spectra of Bremsstrahlung photons. And the bottom panels show the integrated energy spectra. If we compare this figure directly with the source, especially the high energy component, it's actually pretty clear. This part is basically a reflection of the high energy component because this part is more efficient in Bremsstrahlung production. We then simulate the transport of these X-rays in the atmosphere and connect all photons arriving at 35 kilometer altitude. That is the balloon altitude. This figure shows the energy spectra as would be measured by balloons at 35 kilometer altitude. This is the X-ray count versus time, and the bottom panels are energy spectra, time-integrated energy spectra. From this set of parametric studies, we found a lightning discharge and 45 degrees latitude can best explain barrel measurements. And this figure shows the flux of precipitating electrons as a function of time and altitude and L of 4. And the second panel shows the integrated fluxes. To verify if this LEP event or lightning discharge, if it is reasonable, we have calculated the change in transmitter VIF signals. We have simulated the electron density enhancement in the deraging ionosphere using a pretty simple 5-species chemistry model. And the lines here, the structure here, basically shows the disturbance brought by LEP event. And we then propagate VIF waves through these enhanced regions. And this figure shows the change in transmitter VRF signals. We see a half dB change in VRF amplitude, which is pretty typical of LEP events. And this means this lightning discharge is reasonable in terms of VRF response. We then simulate the production and transport of Bremsstrahlung X-rays. This figure shows the production, and this figure shows the energy spectra that would be measured at 35 kilometer altitude. The comparison with barrel measurements is shown in the bottom two panels. The bottom left panel shows the comparison of X-ray pulse. The bottom right panel shows the comparison of energy spectrum. It is pretty clear that the simulated X-ray pulse agrees pretty well with barrel measurements, especially the falling part of the pulse. And also, like, the energy spectrum is also highly consistent. These results led us to believe the barrel measurements are indeed X-ray signatures of LEP event. They represent, to date, the first X-ray measurements of LEP event. But the problem here is to explain barrel measurements, we need a lightning discharge with a peak current more than 300 kiloamps. The lightning discharge we found, the best lightning discharge we found is actually around 45 degrees latitude, most likely from this storm. But we need a peak current more than 300 kiloamps for the lightning discharge to explain barrel measurements. But we cannot find in the detection networks, we cannot find such a lightning flash from lightning detection networks. The largest peak amplitude, the largest peak current we found is around 160 kiloamps. There is there are some reasons for this. I will not go to the details of these, but it's probably due to the detection capability of ground-based measurements, as well as the simulations that we did. I don't know exactly, but these are like Woonen measurements. There are probably some stations around here and somewhere around here. Yeah. Yeah, I don't know exactly the location, but it's actually because VOFs are basically bounced back and forth between the ground and the lower boundary of the ionosphere, so they can propagate for thousands of kilometers with like very low attenuation. These VOFs can directly propagate. Oh, I mean that's what I was explaining was about the detection of deraging ionosphere, but this kind of like measurements is actually also using those VIF waves. For example, using several stations, they can geolocate the location of the nitrogen discharge. Yes. Yes, that's usually what we use, and the map we usually see. Yeah, Navy transmitters, yes. Navy transmitters are used here. The singles are used here for the calculation uh, of change in amplitude. But for this kind of like lightning location, geolocation, this kind of stuff, it's actually using the radio pulses emitted by lightning discharge itself. Yeah. Mm-hmm. Yep. Yep. It's basically the same frequency range. Yes, that's the same. Um, to summarize, in these two studies, we have investigated the production, transport, and redistribution of Bremsstrahlung X-rays in the Earth atmosphere. We have developed a method to estimate the size, flux, and spectrum of precipitating electrons using space-based X-ray measurements. In the second study, we have investigated the first X-ray measurements of LEP event. I still tend to believe so, although we cannot find the source nitrogen discharge. The simulated X-ray pulse and energy spectrum are highly consistent with balloon measurements. It's only like we cannot find the parent nitrogen discharge from ground-based measurements. And that summarizes my talk. Thank you. Yes, the current that is needed to explain barrel measurements is more than 300 kiloamps, which is not impossible, but should be very rare. But there's also some complexity here. So basically, the reason that we cannot find out the parent nitrogen discharge, there are like many reasons for that. One of the reasons is because of the drift loss cone. One of the reasons is because of the availability of energetic particles in the radiation belt. One of the reasons that I tend to believe in is the detection capability of Woonen or some detection network. Basically, the detection capability is found to be pretty low and high latitude regions. And also, like we did a lot of simulations here. We used a total of like 5 or 6 numerical models here. It's very possible that there are like many free parameters here. It's very possible one of the free parameters is not very well tuned, and because of that, our simulation results may overestimate the peak current that is required to explain barrel measurements. Yeah. Yes, something like that. Yeah. Yes. Mm-hmm. Mm-hmm. Yep. I was actually expecting this question. So, as we see from here, the temporal structure of those X-ray pulses measured by barrel can be very well explained by our simulation results. It's only like the magnitude of these pulses. The total X-ray counts is roughly proportional to the square of peak current, lightning peak current. So in order to match the barrel measurements, we need to use a peak current of more than 300 kiloamps. So it's just like the peak current. The energy can be very well explained. The temporal structure can be very well explained. The location can be very well explained. It's only like the peak current. We cannot find a lightning flash with a peak current more than 300 kiloamps from the ground-based measurements. But there are definitely flashes there. Yeah, could be, yes. Yeah, we get it at the right time. Yep. Yeah, actually, for that event, we don't show it here. It's like only like, yes, it's right in time. The short answer is it's right in time. It's only like a few milliseconds prior to barrel measurements. Yep. Mm-hmm. Yes, it is. It's definitely ever observed. Mm-hmm. Oh yeah, that's actually a different topic. It's my PhD thesis. So lightning discharge itself can generate some really energetic particles, electrons, and gamma rays. And these gamma rays can also escape the atmosphere. And these are called terrestrial gamma ray flashes. And these are directly produced by the lightning electric field. But these kind of events are produced by the radio signals of lightning discharge. Mm-hmm. Yes, one is very short pulse, yes. Yep. Mm-hmm. Mm-hmm. Yes, it depends a lot on if the source precipitating electrons are beam or isotropic. It also depends on the energy of those particles. If those source electrons are more beamed and more energetic, those secondary Bremsstrahlung X-rays would actually be more beamed, like forward emitted. Mm-hmm. It's in the, yep. Mm-hmm. Um, yeah, I agree with your this statement. If these precipitating electrons are aurora precipitating electrons, but they are like also like more energetic electron precipitation, or even like relativistic electron precipitation. They are not exactly isotropically distributed in pitch angle, and their energies can reach up to like 10 MeV, and in that case, it can be more beamed than aurora precipitating electrons. Yeah. Yep. Mm-hmm. Exactly. Exactly. Yes. Uh, no one really knows. Yeah. So no one. Mhm. Yeah. Yeah. It's actually still a challenging for satellite measurements because they cannot very well resolve the pitch angle distribution of those particles in the radiation belt. Yeah, so no one really knows if it is like uniform. I mean, it's pretty like isotropic for aurora precipitating electrons, but for more energetic ones, no one really knows if it is like isotropic, sine, or some really weird pitch angle distribution. So that's pretty much my understanding. Yep, yep, exactly. Hmm. Yes, exactly. Yeah, non-collision. Yeah, that's the definition of North cone, right? Yep. Hmm. Yeah, good question. So basically, we compared the results with Fang Annual 2010. Um, we used different models. Fang used a multi-stream or two-stream models, and we use a Monte Carlo model. So the physics is not exactly the same. And also, like the background atmosphere can change or not, the number density. So as far as I know, the background atmosphere density can change the altitude of peak ionization by up to 10 kilometers. So we can easily, I mean, change the background atmosphere and try to match Fang's calculation. Uh, it's something like we probably need to do another test, um, and it's already very close here. Mm-hmm. Mm-hmm. Exactly. Yep. Mm-hmm. Yep. Mm-hmm. Uh, yeah, a factor of 2 and 5 kilometers, something like that. No. Mm-hmm. Mm-hmm. Yeah. Yep. Mm-hmm. Yeah. Yeah, this is actually something we are doing right now. So we have actually quantified the dependence of ionization production on the background atmosphere density, something like that. For example, I can run 100 AMSIS atmosphere and calculate the ionization. Yeah, yeah, exactly. Mm-hmm. Yes. Yeah, sure. Yeah, sure. Mm-hmm. 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 I see. Mm-hmm. I see. Yep. 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 Mm-hmm. Yep. Thank you for the suggestion. Actually, it'll be even sweeter to compare directly the simulation results from our models with your model because both are Monte Carlo based. Yeah. Oh, that would be cool. It is. Mm-hmm. Yeah, we actually take the mirroring effect into account in this calculation. Exactly. Yep. 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 Which is just like not accurate. Yep. 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 Thank you. Thank you.好，谢谢你。然后我是想回国，但是现在还不太确定。然后现在好多事情，我也不知道现在是这么。对，现在还在想到底要干什么接下来。对对对，谢谢女老师，真的，Thank you，See you。徐渭，对，哦，你好你好。哦，这样是吧？哦，你是做相似的东西吗？可以可以。Yeah, it's really nice meeting you. Yeah, sure. Yeah, I read a lot of your papers, including the glow model. Actually, I was
That's what I was saying. You could do this with glow.
Yeah.
I mean, except for the magnetic part.
Exactly.
But you can do the collisional part with glow.
Mm-hmm.
It may not be. It should be fairly accurate within the assumptions
Exactly.
that are made.
Mm-hmm. Do you know Jianqi? Jianqi Qin.
I must.
Yeah, actually.
But I'm not sure.
Yeah, we are from the same lab. We're doing PhD study. He's working on some satellite measurements of some oxygen lines using the glow model. Yeah, we are actually considering adding some emission lines to the glow model.
Oh, okay.
Yes, still working on that.
Yeah, if you have anything.
Yeah, definitely need your help.
You just send it to me.
Yeah, sure. Thank you so much. 现在在那个还在 CAR Aerospace 那边，CU 那个，对对对。 CCAR。
CCAR。
对。